This is the Level 2 2016 Waves exam. For this question, for this video, I'll be working through question 2. Question 2. Tim looked at the pond in the garden and noticed a pattern in the water caused by the wind. The diagram below shows a simplified pattern of the water waves being refracted as the depth of the pond of the water in the pond changes. Refraction occurs at the boundary between two depths of the pool. Incident waves are on the left at the boundary, and that's really about it. Right, so this is, you got one medium, the other, as we can see, it must be going fast in here and slowing down here, because here the waves are getting closer together. So I'll just write fast just to begin with. Slow, so as they slow down, the wave fronts get closer together. So this will help us for later. Draw an arrow to mark on the diagram the direction of the incident wave as it reaches point X. So we can think about these as, waves at the beach. These are the waves, coming in one wave after the other, and the direction of them is obviously perpendicular to the wave front. So using our ruler, I'm going to do it perpendicular to the wave front. So that's the incident wave coming in. Make sure we put an arrow on it, and now we need to have our refracted wave, or the outgoing wave, perpendicular to the wave fronts, making sure to have the arrows to show the direction. There we go. There's question A done. B. Which property of the wave does not change when it's refracted? So that's frequency. Frequency. The reason for that is energy conservation. Waves propagate energy either through a medium or through space if they're electromagnetic wave. So they're a propagation of energy. So if the wave slows down or speeds up, the wavelength and the velocity can change, but frequency must remain the same for conservation of energy. Right, so the wavelength of the wave gets smaller as it enters B. Explain what this tells you about the speed of the wave in medium B. Well, I've already said in medium B is going to slow down, or it's going to slow down, because we can see the wave fronts getting closer together. But we can say V equals F lambda, so that's the wave equation, comma, F remains constant. We've said that up there before, constant, which means I'll just put lambda gets less or smaller, so velocity must increase. No, it must decrease. What am I talking about? Decrease, that isn't. There we go. So if lambda goes down, velocity goes down. What am I talking about? Yeah. And that's because the frequency remains the same. There we go. And we've said it decreases up here as it slows down. Right. Let's shift this up a little bit. If the wavelength of the wave in medium A is 3 meters and the speed of the wave in the medium A is 3.3 meters, calculate the wave speed in medium B if the wavelength of the waves in medium B is 0.2 meters. So it's a good idea to write V equals in medium A 3.30 meters per second minus 1, lambda equals 0.300 meters. Over here we have wavelength equals 0.200 meters and velocity equals question mark. So on your formula sheet, if you take a look, we have, here's the wave section, we have N1 over N2 equals V2 over V1 equals lambda 2 over lambda 1. N is your index of refraction, which is just, it's relative speed, sort of. So the higher the refractive index, the lower your wave speed is through a medium compared to a base medium or a medium which fixes the speed, and everything else is a comparative sort of measure. Right, so we're going to use this formula, but we're going to use V2 over V1 equals lambda 2 over lambda 1. So we're going to write V2, I'll just move this up a bit, over V1 equals lambda 2 over lambda 1. Notice that this is v1, lambda 1, lambda 2, v2. What we're trying to find is we're trying to find v2, so we're going to rearrange. So all we need to do is times both sides by v1. So if I times this side by v1, it cancels this out, moves it to the other side. v1, in other words, v2 is equal to lambda 2, which is 0.200 meters, divided by lambda 1, which is 0.300 meters, times v1, which happens to be 3.300 meters, no, just 10, meters per second minus 1, which equals 2.20 meters per second minus 1, which is the velocity. Notice I've given 3SF because they've given me all their values to 3SF. Next question. The pond is large enough that other wave effects can be seen by Tim. At one end of the pond there are two large rocks that can be made to partially block the waves, and they move from left to right. A water lily is floating beyond the rocks. By changing the position of the rocks, Tim can cause the water waves to move the floating lily. Name the process by which waves could reach the floating lily. And it's called diffraction. Diffraction. Here we go. And it looks a little bit like this. So here we have a large gap, which means we're going to get less diffraction. You're going to get a little bit of, and so I'll just draw it and then go over the key points. I'll try and be neat. The neater you are, the easier it makes on yourself. There we go, so that's the first one. Here we go. So as we can see, position B causes more diffraction. Granted, position A still causes some diffraction. This here would be, the waves wouldn't be as intense, or the wave fronts. But if you try this in an actual pond of water, if you do this in a ripple tank, you'll find that the lily will move pretty much both as much position A, position B. But position B, because the gap width is similar to the size and wavelength, you will still get diffraction. One thing to note is to put in that each of these, the wavelength doesn't change. So if you're not very good at drawing, it pays to put in that the wavelength is the same. Otherwise, you can get marked down for not very good drawing like me. Right, so complete both diagrams to show the pattern created by the waves as they pass through the gap between the rocks, position A and position B. Yeah, we've already done that. Use your answer to part 2 to decide whether the waves reaching the floating lily using rock, whether the waves reaching the floating lily using rock position A or rock position B. Give a comprehensive explanation as to why this rock position affected the waves more than the other rock positions. So I'll just start writing. We see that waves will reach the lily, spell that correctly, using, that's not how you spell using, I don't need S there, rock position B with greater strength, or magnitude, or whatever synonym you can have for that word. This is because the closer the gap size is to the, I'm going to say lambda, but it's wavelength, the larger the diffraction observed. Position B is similar in gap size to lambda, so will diffract more by comparison to A. Right, so that's probably not the best answer, but it sort of gets the gist of things. The waves, they will reach position A, but B, it'll be slightly more slightly more intensity will reach there. That's probably not even the right word for it either. But either way, the point of this is to get across that if the gap size is similar to the wavelength, more diffraction, or the diffraction pattern is more pronounced. And if you want to look it up, there's something called Huygens principle. I don't know if I'm pronouncing it correctly. It is spelled correctly though. Huygens, Huygens principle. Huygens principle that demonstrates or that clarifies the diffraction